going to continue going over the open book test for calculus units 1 through 3. Now, we're looking for the limit, and the limit we know is equal to the function value as long as it's continuous. And we know that it's everywhere continuous unless there's a denominator. If that denominator was 0, then there would be a discontinuity, or if there's a square root, we would look for what would produce the square root of a negative. So to see if this c that x is approaching is within the domain of the function, so that we will know if the limit is equal to the function value, we need to really find the domain. So let's find the domain, and this is just a good exercise for us. For this situation to create a 0 in the denominator, then we would basically set our denominator equal to 0, right? We'll come over here to the side and do that. X squared minus 9 cannot be equal to 0. We're trying to find the things that x cannot be. So the denominator cannot turn into a 0, so we would add 9 to both sides. We would have x squared cannot be 9. So when we take the square root, we get that x cannot be a negative 3 or a positive 3. X cannot be plus or minus 3. Remember, the way this would look would be negative infinity. Whoops. It would be, if we wrote it as a domain, it would be from negative infinity to negative 3, from negative 3 to positive 3, and from positive 3 to positive infinity. Now, these are open intervals with the open part. So if my domain, if my target point lies within the domain, then the limit is equal to the function value. Well, 3 is not in the domain. 3 is excluded. Therefore, we can look and say that the limit as x approaches 3 is not the same as f of 3, because 3 is not within the domain. So you can't just do a direct substitution. There's a discontinuity in the graph. That means if we graph this, and you realize we've got an x over an x squared, so the idea we would have is maybe some kind of rational situation, because that would kind of reduce in form to 1 over x, maybe. And so we got something like that going on. So somewhere in this situation, in this graph, let's just say it's like this, and it may not turn out to be that. Somewhere in there at 1, 2, 3, there's a hole in the graph. Now, the idea of what we're going to do is we're going to take this and hopefully do some cancellation, some reducing kind of thing, and really get it down to that form. And what we're going to do is create a g function that's exactly the same as the original f function at every point except that one. And in that g function, that point will actually exist. If that's true, then we would know that the limit on the green one, we can see that that limit would be the function value of the blue one, you see. Okay? So we do that by what? How do we create a g function that's equivalent to the f function in all points but one? Right, we factor out in the g function. So in this f of x function, so in this f of x function, x minus 3 equal x squared minus 9, we know that this is the difference between 9, 3. It's the difference between x squared and 3 squared. What does the difference between two squares factor into? The binomial conjugates x and x minus 3. We have an x minus 3 factor on top. And so we can see that those x minus 3 factors cancel. So we end up with 1 over x plus 3. And so basically we removed that discontinuity where that hole was. We've now created a g function where that discontinuity is removed. So we know that the limit in the f function is equal to the function value in the g function. So what we're going to do then is this is now my f of g. That is equivalent to my f of x in all points except this one. So I'm going to substitute my target point into my g function. I should have a g of x there. Too many letters, I'm getting confused. G of x. And so that would give me 1 over 3 plus 3, which is 1/6. Any questions on number 9? So we identified the domain of that function, and we said, well, this target point 3 is not in the domain. So the function value doesn't exist. Therefore, it is not continuous. Therefore, we know that there is a limit, but we can't see it because it's not equal to the function value. So to find that limit, we factored. We created a g function by factoring that was equivalent to this f function in all points except that point right there when x is 3. And therefore we could find what it's approaching in the g function by knowing exactly what that point is in that f function. Any questions on number 9? Okay. Well, number 10, there's a possibility of a limited domain because we see what? The square root. Now, what's inside that square root, that x plus 5, what must be true about it? It must be greater than or equal to 0. It's got to be a positive number. And so if we were to subtract, we would have that x must be greater than or equal to -5. So my domain would look like, it would look like this. Now that's just the numerator. There's also a denominator problem. And we know in the denominator that the denominator, x minus 4, what about it? It cannot be 0. It can be anything but 0. It cannot be 0. So if we add 4 to both sides, we get x cannot be 4. Well, when we put those ideas together, then it looks like this. To satisfy both situations, then we can go from -5 to 4 not included, and then from 4 to positive infinity. Sorry about my infinities. So we see that the 4 is excluded from the domain. Therefore, we cannot find the limit by finding the function value because it's not continuous at that point because that's not within the domain of the function. We know that the limit value is the same as the function value only if it's continuous at the point. So what do? Well, our only choice so far is to create a g function that's equivalent to that f function in all points but 1. So we have f of x is equal to this right here. Now, how are we going to create a g function in this situation that's equivalent to the f function that might get rid of our problem? Well, remember when there's a radical involved, we rationalize the numerator. which is not normal. It's unsimplifying it, but it will help us with our problem. So to just manipulate this into a form that might get rid of our problem, we're going to multiply the numerator and denominator by the conjugate of the numerator, which means we change that sign right there to a plus. Now, we know that when we multiply binomial conjugates up here in the numerator, the result is the difference between the two items squared, which gives us x plus 5 minus 9. Agree with that? Which is going to turn into x minus 4. Now, I'm just going to leave that hanging a second. So if we continue with the numerator, we're going to have x plus 5 minus 9 is x minus 4. And we see an x minus 4. You don't want to distribute this because we want to see that common factor of x minus 4 have the ability to cancel out. So we're going to multiply out the numerator, but we're going to leave the denominator factored in hopes that we see a common factor that will drop out of the picture, which it did, which removed our discontinuity of 4. So we created a g function that is equivalent to the f function in all points but one. Therefore, we can find the limit in the f function by finding the value of the target point in the g function. So we're going to take the 4 and plug it in the g function to get the limit in the f function. So square root 4 plus 5 and then a plus 3. So we have 1 over square root 4 plus 5 is 9. Square root 9 is 3. And 3 plus 3 is 6. So we get 1/6. Any questions on number 10? Now, I want to go back to number 9 and try to take a look at this graphically and see what happens with the graphing calculator. First of all, any questions? Everybody understand all that? Okay. All right. So let's just look at number 9. We're going to go to the graphing calculator and we're going to type in the f function. Okay, so f of x is equal to this, which we're going to put in y equal. So we're going to go to our graphing calculator. We're going to go to y equal. We're going to put in the numerator, open parenthesis, it was it x minus 3? So we're going to have x minus 3, close, divide, there's my fraction bar, open, x, I missed it, sorry, x squared minus 9, close. Now, if I hit graph, there's that rational. It shifted with the minus 3 when I just drew kind of a parent function to start with. Now, if I hit trace, I'm going to move over. Which one I move over? Where was the discontinuity at? Positive 3, remember that? So let me go to, I'm just going to hit table, okay? Second table. Notice when we get to the 3, there's an error. because that's where my division by 0 was. There's a discontinuity. I could trace to it, but watch this. Watch when I go to that function, that g function that we created after reducing. What did we end up with after that? 1 divide open x plus 3. Wasn't that it? So that is the g function that was equivalent to the f function in all points but 1. Now when I hit graph, it's going to graph them both. And what you should notice is the second one's right on top of the first one. You're not even going to see a new graph, okay? So we hit graph, and there they are right on top of each other. So the g function is identical to the f function in all points but 1. Now watch when I hit second table. Oh, it's right here. Yeah. We've removed the error by producing a g function equivalent to the f function. Now, this is interesting too. You can see from the table very clearly that we have removed the discontinuity. But also let's look at the idea of limit. X approaches 3 in the y function. It's doing exactly the same thing in the g function. It's obvious here what y is approaching, what y is as x approaches 3 in the g function, and therefore it's obvious that that's what it would be approaching there in the f function, you see. So we found it by direct substitution by creating a g function equivalent to the f function in all points but 1, and we didn't have to just keep working our way closer. We didn't have to do the 2.1, 2.2, 2.9, 3.1, all that stuff. Okay? Any questions on that? So I wanted you to see the visual of what we're doing as far as removing the discontinuity. All right. Okay, so that brings us to number 11. Now, number 11, what is this saying right here? Good. So it's saying as it approaches -4, and when we think about the graph, this is the negative side of the graph, and this is the positive side of the graph. So here we would say from the left, and here we would say from the right. As we approach let's just call this my C. As we approach C from the positive side of the axis, from the right side, or as we approach C from the negative side of the left side. So we understand that. Okay, so this is saying that we're approaching the -4 from the negative side of the graph, or from the left of the -4. Okay? Now, if you plug in -4, what are you going to get? You're going to have a division by 0 error. So we know that at -4, there's a discontinuity. We may try to remove that discontinuity. Let's see if we can remove it by factoring. We've got an x, and then we have x plus 4 times x minus 4. The discontinuity is not removable. Therefore, the limit as x approaches -4 from the left, maybe from the left might exist, but the limit itself does not exist. At least we can't find it by trying to create a g function equivalent to the f function, so we're kind of stuck. So let's graph that and just take a look at what this thing's going to be like. X over x squared minus 16, just so we can get a picture of this situation. So I'm going to do second quit. I'm going to do second plus 7, 1, 2. Have to go slow on this simulator. Enter clear, it'll freeze up on me. Okay. Now, so we're going to go to y equal. what was my equation again? X divide, is that correct? X divide, open, x squared minus 16. And we'll hit graph. Now, it kind of repeated itself. What was our target point? -4. So let's hit trace, and let's just kind of get our little arrow going. I'm going to get way over here. Okay, so we're over here at -8. See that? -8. Let's approach -4 from the left. As we approach -4 from the left, now look what, well, we're getting closer. -4.8, we're at -0.6, -0.7, 1, 2, 11. It's getting huge. Well, let's say we want to get a little closer. Let's go to second table, and we want to approach -4. Let's go to second table set, and what I'm going to do is I'm going to start at -4.01, and I'm going to make my table change 0.001. Okay, so we're going to creep into it. And then I'm going to hit second table. I missed. Second table. I missed again. Second table. We're going to get there. There we have it. So I didn't go where I wanted to go. I want to increase by, I need to increase by 0.01. That wasn't very smart. Second table set. Wasn't thinking good enough. Okay. Second table. Here we go. All right. Let me go up a little bit. Well, we were at 50. Let me add increments of 0.1. I'm not getting where I want to be. I'm not sure why my thinking is not working. Oh, here we are. That's where I wanted to be. That's what I wanted to see down here. Okay, I'm fine. -3 something. Let's just throw in a point. I'm making a mess out of this video, but that's okay. Let's start at -4.001. Did I get to that? What did I do? Okay. And let's do 0.001. Second table. Now we got big numbers. I was trying to get you some bigger numbers. Now we're at -500. Okay. Now let's go to table set. Let's 0.0001. And 0.001. And second table. And now we've got, I must have missed my 1. Wow. the discontinuity was at -4, so why did I end up with that? Okay, well, I've spent too much time on that. We're getting bigger, bigger, bigger. I obviously made a mistake somewhere in typing that in. But let's just look at this graphical part. I'm just going to go back to graph. So we can see that's what's happening as we approach the -4 is that we're approaching infinity. Now, the question is, does the limit itself exist? Does the limit exist? Well, from the left, what's it approaching? So as we approach -4 from the left, then we're approaching negative infinity. As we approach -4 from the right, we are approaching positive infinity. Now, the limit itself doesn't exist, because for the limit to exist, it has to approach the same thing from left to right, and it cannot approach infinity. But we can still use the terminology. We can still use the terminology that as x approaches -4 from the left, then it's approaching negative infinity. We can still say that. We're not talking about the whole limit as x when the target point is -4. We're saying as we approach it from the left, what's happening? It's approaching negative infinity. As we approach it from the right, what's happening? It's approaching positive infinity, but the limit itself does not exist at all. Okay? All right. Trying to show you that graphically, and I should have pre-done some numbers. I was really doing crazy decimal stuff backwards there. But anyway, so let's go back and just pull out the worksheet then. So what we're saying is, from this graphically we saw, and we'll do a little graph here just so you can see it. When we went to -1, 2, 3, 4, there was a vertical asymptote there. And then my graph would have done something like this. And so we said as x approaches -4 from the left, then it's approaching negative infinity, which is the answer to the question. As x approaches -4 from the right, we can see that it approaches positive infinity. We would say the limit as x approaches -4 does not exist. Because as you approach from left to right, it's not approaching the same thing. And as you approach that target point -4, it's going into infinity, which is one of the 3 disqualifications for it to be a limit. Remember, for the limit to exist, number 1, it must approach the same thing from left to right, so we broke that rule. Number 2, as you approach it, it cannot go into infinity, so we broke that rule. And the third rule is that as you approach it, it cannot oscillate between 2 fixed points. So we broke 2 out of the 3 rules for it to be a limit. Any questions on number 11? We did a little bit of table stuff where we could start seeing, okay, as we get closer, it went from, point something to a bigger point something to 1 to 11 to 50, and then we changed some numbers and got in the 500s, and we could have got bigger and bigger and bigger. Okay? Any questions there? Sometimes what I was trying to show you, the graphing calculator will help you visualize what we're doing here. All right. Now, the question here says, find the x values, if any, at which f is not continuous. Which of the discontinuities are removable? So we want to find discontinuities, and we want to see if we can remove those discontinuities. Now, what would cause a discontinuity here? A division by zero error. So we would say, okay, x squared minus x cannot be 0. X squared minus x cannot be 0. And so we would have, if we factored out an x, right, there's a common factor x in those, then you would have x times x minus 1 cannot be 0. Everybody agree there? From this one, we would have that x cannot be 0. And from this one, we would have that x minus 1 cannot be 0. Therefore, x cannot be 1. So we could say f is not continuous at x equals 0 or x equal 1. Understand that? But then we want to know which of the discontinuities are removable. And so we're going to create a g function equivalent to the f function in all points but 1 by factoring. Remember that factored into x times x minus 1. By factoring the, that was weird, x times x minus 1. By factoring, the x's drop out, and so I have 1 over x minus 1. So which of the two discontinuities did we remove? This one, which was x equals 0, and so x equals 0 is removable. Any questions on number 12? So we identified the discontinuities and determined which of those discontinuities were removable. If we have a removable discontinuity, what good is it for us to know that so far? Well, it allows us to find the limit at that discontinuous place by plugging our target value into the new g function. Okay? If it's non-removable, even creating a g function didn't help us find a limit by plugging into it, because there's still a problem in this new g function. There's still a problem at x equal 1. In the f function, there was a problem at 0 and 1. We removed it from the g function, but we couldn't remove the 1 from the g function. All right, any questions on that? All right, so number 13. Number 13, the two things that can create a discontinuity again are a division by 0 and the square root of a negative. We do know that to be continuous, what three things must be true? The f of x must exist at the target point. The limit as x approaches c must exist at that target point. And the limit must equal the function value at that point. All right. Now, the reason we're saying that this is discontinuous is because the function value doesn't exist. We're finding the domain, and we're saying that the domain excludes those values from existing. Okay, so to have a division by 0 problem then, the denominator x squared minus 36 then we know cannot be 0. If it was, we would have a division by 0 error, which would create a discontinuity. So then we would solve for the x's that would produce that problem. So we'd have that x squared cannot be 36. So we would take the square root of both sides. And we would have that x cannot be plus or minus 6. X cannot be plus or minus 6. So if we write this out, we would say that the function, how did I write it last time? I forgot what I wrote. That's better. Thank you. Wow. F of x is not continuous at negative 6 and 6. F of x is not continuous, I should say, at x equals 6 and x equals negative 6. So we found two discontinuities because they create division by 0 errors. Now, we need to see if either of those is removable, and we're going to do that by factoring. In the numerator, we have an x minus 6. The denominator is the difference between x squared and 6 squared, which is 36. So it factors into the binomial conjugates, x plus 6 times x minus 6. We have a common factor of x minus 6, which cancels. And so my g function that's equivalent to my f function in all points but 1 is 1 over x plus 6. So which of the two discontinuities did we remove? No. If it's x minus 6, then x cannot be 6. The other one. You got to be careful there, right? Okay, so x equals 6 is removable. Any questions on number 13? All right. Number 14. Number 14, if we had a division by 0 error, we would have a discontinuity. So the denominator x squared plus 5x plus 6 cannot be 0. Now, remember that in a quadratic, if your a is 1, then you can factor by coming straight down into your parentheses with an x. But if a was more than 1, we would use the AC method of factoring, multiply a times c and all that. We'll talk about that some more later. But you understand when a is 1, you can go straight in there with your x's. And then what do you think? What are you going to be thinking? What can I multiply to get the c value of 6? That's a 6 right here. I don't want that to look like a b. And then what can I add to get the b value of 5? So we think, what can I multiply to get 6 and add to get 5? Well, 2 and 3. So I'm going to have a positive 2 and a positive 3. You remember that when a is 1. Now, if a is not 1, then you can use the AC method of factoring, which we taught you. It's on page 213 of my Algebra 1 book. Or you can use the quadratic formula. Remember it? X equal negative b plus or minus the square root of b squared minus 4ac all over 2 times a. So if all else fails, use the quadratic formula. But we would fail if we did because, well, we could kind of go backwards. But we really need to be able to factor. Because if we're going to remove the discontinuities, we don't just need the solutions, we need the factors. Okay, so we now have x plus 2 over x plus 2 times x plus 3. And so those cancel, and we have 1 over x plus 3. So right here, we know that x cannot be what? Negative 2. Here, x cannot be negative 3. So we would say that f of x is not continuous. At x equal negative 2 and x equal negative 3. And then we would know that the x equal negative 2 is removable. Remember, we call these discontinuities, right? Discontinuities. With the x equal negative 2 is a removable discontinuity. Okay, any questions on that? Appreciate your attention.